Hello and welcome everyone to another episode of Algorand Developer Office Hours. I'm your host, Ryan Fox, and I am a developer advocate here at Algorand. I'm thrilled to be joined today by a couple of developers at Tinyman, Fergal Walsh and Effa Olga. They are respectively the CTO and the lead backend developer on the Tinyman project. So today we're going to learn how Tinyman are building their decentralized, secure pooling and swapping protocol atop Algorand. You know, it's already running on testnet, and you may be familiar with their permissionless automated market maker. Today, Fergal and Effa will share about their design and the implementation, which provides guaranteed liquidity to all market participants. So, Effa and Fergal, welcome to the Developer Office Hours. Glad you're here.
Thank you, Ryan. It's great to be here.
Outstanding. Well, we always like to know where in the world are you joining us from?
I'm joining from Ireland.
I'm joining from Istanbul, Turkey.
Outstanding, guys. Well, thank you both for being here. We look forward to learning more about Tinyman. Take it away, Fergal.
Thank you. Okay, so welcome to our talk about Tinyman. At its core, Tinyman is a permissionless, trustless, decentralized trading protocol on Algorand. So throughout the session today, we'll explain what this really means, and hopefully by the end, this sentence will make perfect sense. But Tinyman, as a project, is made up of three core components, one of which is the protocol, but there's also the web app, which is the main user interface to the protocol. And then there's the analytics service, which powers the statistics side of things. Before we continue, we'd like to introduce our team. So myself and Effa here are talking today on behalf of a team of 9 people in total. And so we're a team of builders. Some of us have been working together for more than 5 years. And we see ourselves as Tinyman's friends, helping Tinyman to develop his dream. And so we are a team of designers, front-end engineers, back-end engineers, smart contract engineers, QA engineers, and marketing. So let me introduce Tinyman. So Tinyman is out on the quest. Tinyman wants to buy some coffee. And the coffee costs 1 B, one unit of asset B. But Tinyman only has asset A in his wallet. So what is he going to do? He needs to go on a quest to find some asset B so that he can buy this coffee. So Tinyman goes out in search for some asset B. And he comes across the Binance exchange, a centralized exchange where he can trade his asset A for asset B. Seems like a good idea. So he can sell some of his asset A and get some asset B and then buy that coffee. But upon entering the exchange, he realizes that it's just too expensive. It's going to be really slow and it requires a lot of trust. Maybe he's going to sell his asset A but not get any asset B in return. Or maybe it's going to take a week to get his B and then he's not going to get his coffee. So this doesn't seem like a very good solution. So desperate Tinyman goes out in search for another solution. And he comes across a decentralized exchange. And through this decentralized exchange, Tinyman is able to atomically swap his asset A for asset B in a completely trustless manner. So he can get the assets he needs, he can exchange the assets he is able to sell, and he can do this in a fully secure way. And now that he has his asset B, he can go back to his original quest and get his coffee. Tinyman's happy. So this is the basic concept that we are introducing today, the idea of a decentralized exchange. So the Tinyman app will be the first decentralized exchange on Algorand. And this will be a way for users to obtain assets by selling one asset to obtain another asset to use in various different projects. So in real world terms, what does this look like? Well, we have this web app where you can simply exchange assets one for another. You put in the amount that you want to sell, and then you get your quote for the output amount, and you can swap these You confirm your swap, and then you sign it with your wallet. You can use the MyAlgo wallet, Algo Signer, or the mobile wallet. You confirm the transactions, and in a few seconds, your swap is complete. It's all very simple. But we're going to explain what goes on behind the scenes. Also in the web app, there is an analytics section, and this allows users to make informed choices about the swaps that they're going to make. So they can check through this analytics, they can check the liquidity of assets on the Tinyman system. They can check the volume and the price changes and all sorts of things like this. Effa is going to talk more about this Tinyman analytics section later. So why Algorand? We probably don't need to explain this to this audience. Everybody here knows that Algorand is fast, it's cheap, it's secure, it's reliable, it's green, and no front running and low possibility of MEV. These two are extremely important for a decentralized exchange, especially in AMM. So it's going to be interesting to see the effect of this on Algorand. So we're going to start with some basics about decentralized exchange and AMMs. So a DEX, or a decentralized exchange, is this idea of an exchange that exists wholly on the blockchain. So it's completely decentralized. There's no centralized authority that is responsible for the liquidity in the exchange. And then an AMM is an automated market maker. And this is a particular type of decentralized exchange. And an AMM uses this concept of pools. So in an AMM pool, we have two assets, which are held in two assets that are held in a pool. And if you want to buy one of these yellow assets, then you need to provide an equal value of the green asset to the pool. So the algorithm behind this is called the constant product market maker, and the constant product market maker has a very simple formula, which is x multiplied by y equals k. So what does this mean? It means that the product of the asset reserves, so the total of the asset 1 and asset 2, the product of those must remain constant. So if I make a swap, the product must stay constant after that swap. It cannot be reduced. So the total value that is held in the pool must stay constant over time, unless, of course, more value is added to the pool. And yes, so swaps must not cause the pool to lose value. So we can look at an example of this to maybe explain it a bit more clearly. So here we have two assets in a pool, asset A and asset B, and they have a ratio of 1 to a quarter. So we have 100 of asset A and 25 of asset B, and the product of these is 2,500. So let's say I take away one of asset A. Now there's only 99 asset A, and now we have a product of 2,475. And this is not an allowable situation because the product has reduced. So we need to either add back asset A or else add on the asset B side. So if we're trying to remove from asset A side, then we do need to add back on asset B. So we add back a quarter of asset B. And now the product has returned to 2,500. We can look at another scenario where we want to buy some of asset B. So now if we remove one of asset B, the product has reduced to 2,400. So we need to add back on asset A side, and we add 4 and a bit. Now, you might notice that the ratio, it wasn't exactly 4 to 1. And this is how the AMM formula works, that you don't get the same price or the same ratio all the time. It depends on the amount that you're swapping. So we can look at an extreme example of this. Let's say I want to purchase 2/5 of the pool on the asset A side. How much asset B am I going to require to sell? Well, you're going to have to sell. You're going to have to provide 16 and a bit of asset B, which gives you an effective exchange rate of 1B to 2.5A instead of 1 to 4. So this is what's known as price impact. So there's a high price impact because the liquidity here is low. So we're trying to buy a huge portion of one side of the pool, and so the price that we get is very poor. But the constant product formula ensures that the value of the pool remains constant over time, even if somebody does buy a huge portion of the pool. So we need our pools to be very liquid. We need lots of each asset in the pool in order for this to work effectively, so that if someone wants to make a large trade, it's still only a small proportion of the whole pool. So this is where poolers come into it. So who provides these assets to the pool? Well, the answer is poolers. So poolers are another class of users in this system, and they provide assets to the pool in exchange for pool tokens. So if there was a total of 50 pool tokens issued and you hold 50 pool tokens, then you have 100% share of the pool, obviously. But if there's a lot more assets added to the pool and people get pool tokens in return, so now the total issued pool tokens is 800 and you still have 50 tokens, then you own 6.25% of the pool. So you own a small share of the pool as an individual pooler. So this is how various users come together to contribute assets to the pool in order for this pooling concept to work. And so the pooler can remove the liquidity from the pool at any time by burning some or all of their pool tokens. So if they were to burn 5 of their pool tokens, then they can retrieve 20 of their asset A and 5 of their asset B. Or they could hold them. They could keep them in the pool, because by keeping them in the pool, they get some reward. So they earn 0.25% of all trades that happen on the pool. And so if you keep your assets in the pool and you hold your pool tokens, then over time, the value of those pool tokens will increase. So you originally put in 100 of asset A and 25 of asset B, but now your pool tokens are worth 104 of asset A and 126 of asset B. Unfortunately, it can also go the other way if there's an extreme difference or an extreme change in the price of the assets, and so you can end up with a large amount of asset A and a small amount of asset B. There are also various other risks involved in providing liquidity for the pool, so it's very important to read up carefully on this concept before doing so. You need to know what you're doing, so do your own research, please. Okay, so I'm going to talk about how we designed an AMM on Algorand. So you might be familiar with this AMM concept already, and you might know, for example, that Uniswap is an example of an AMM on Ethereum. It was the first AMM, and there has been many clones of Uniswap and clones of Uniswap on Ethereum and clones of Uniswap on other chains. What we have here is not a clone of Uniswap. So this is an AMM built and designed specifically for Algorand. So it's the AMM concept, but it's re-implemented from scratch. It could not be directly cloned on Algorand because Algorand does not use the Ethereum virtual machine. It uses the AVM, which is entirely different and entirely better. So also, this is an AMM on Algorand designed for the Algorand virtual machine as it was in around April 2021. So just a few months ago, but a lot has changed since. So specifically, it's designed for TL3 and has some small sprinklings of TL4 added later. But it is not designed for the version of AVM that was released just a few days ago. So back to our basic concept. So we have pool tokens, we have 2 different assets. So on Algorand, we have a contract account where we represent our pool as a contract account, and we keep our unminted supply of the pool tokens in that account, and they are just a ASA, an Algorand standard asset. And then this account also holds our reserves of our asset 1 and 2, which are also ASAs. So we can imagine what the protocol for this might look like. So you can think of a swap Well, a swap is basically two transactions. It's a transfer of one asset from the swapper to the pool, and then it's a transfer of assets from the pool to the swapper. And this is implemented as an atomic group. So this means that if one of these transactions fails, then all of these transactions fail. So you can't be in a situation where you have sent your assets to the pool, but the pool has not sent you back the assets in return that you signed for. Or you couldn't be left in a situation where you're waiting 2 weeks for your assets to be given to you. And so the responsibility, so there's a contract here. So the pool itself is a contract account. And so the contract needs to enforce, it has some responsibilities, and it needs to enforce that this x multiplied by y equals k is always true. So it needs to be sure that the product of the reserves remains the same before and after a swap operation. And it should only allow minting of pool tokens in exchange for the correct amounts of assets 1 and 2. So you shouldn't be able to just withdraw pool tokens randomly, because those pool tokens are worth a share of the pool. They're valuable assets. And it should only allow withdrawal of assets 1 and 2 in exchange for the correct amount of pool tokens. And that's the basic responsibilities of the contract. So we could imagine a contract that looks something like this. So we get the asset 1 reserves, we look them up on chain, and get the asset 2 reserves, we calculate k. Then we calculate the new k by looking at the asset 1 reserves and adding the input amount, and the asset 2 reserves, subtracting the output amount, and we assert that the new k is equal to the old k. This is assuming there's no swap fees involved, so we're assuming that k should always equal new k. And this is the basic concept, except that this won't work. So this won't work in a stateless contract. We can't have a contract account. So assuming that we were back in April 2021, we can't have a stateless contract account that can, a stateless contract that can look up balances on chain. So we need to introduce a stateful app into the mix here. So we need to create another transaction, which is going to call a stateful app, and that stateful app is going to do the balance lookups. And then we need to organize this so that these group of transactions are always called together. There is another issue here also, that each of these transactions is going to cost some transactions fees. So it's going to cost some algo. And one of these transactions is signed by the swapper, so they're paying for it. But 2 of these transactions are now signed by the pool. And so somebody needs to pay for these. As a decentralized permissionless protocol, Tinyman can't pay for these. Tinyman doesn't have any algo to pay for these. So the user, the swapper, needs to pay for the transactions that are made by the pool. So we need to introduce another transaction into this group. So this is a payment from the swapper to the pool of the amount of algo that's going to be spent in transaction fees in the subsequent transactions. And now we have our final transaction group for the swap operation. And if we sign this in the mobile wallet, we can actually see that these are the exact transactions that we would be signing. So we have a payment to cover the fees of the subsequent transactions. We have an application call to the stateful app. And then we have a transfer of one of the assets to the pool. And then we have a transfer to the user account of the other asset. And so now our pool logic signature is a bit different. Now its main responsibility is to ensure that to ensure that the transactions made to this contract account always include an application call to the Validator app. So it ensures that the sender of that transaction 1 is always an application call. The application ID is always the correct Validator app, and that the sender is the contract account itself. And then it also needs to ensure that the fees are paid in transaction 0. So again, it needs to make sure that the pool is not paying the fees for itself. It needs to make sure that the transaction is sending is sending the algo to the pool, and it needs to make sure that the amount is sufficient to cover the fees which are calculated elsewhere. And then the Validator app, well, now it's just responsible for asserting K. So get the product of the asset reserves, then calculate the new K after adding the sell amount and subtracting the buy amount, and asserting that these are still equal. And this works perfectly in your demos on testnet. This wouldn't work on mainnet. This would completely fail with concurrent users and would be massively frustrating for users. Why? Well, the answer is slippage. So what is slippage and what can we do about it? So to explain slippage, so the client, so our web app, looks up the pool reserves from the pool account, and it generates a swap quote. And then the user accepts that quote and they sign the transaction, and the client submits the transactions to the blockchain. And then the transactions get executed by a node, and then the user receives confirmation. Okay. But between steps 1 and 4, multiple rounds may have passed. The user may have kind of hummed and hawed about making their transaction. They weren't sure if they wanted to confirm it or not. They may have left the window open for a while and they come back. Or even in the space of a few seconds, the pool reserves might change because of other activity that happens on the pool. So if anyone else makes a swap or adds liquidity or removes liquidity, then the pool reserves change and the quote is no longer valid. And so we say that the exchange rate has now slipped. And the system has no tolerance, like zero tolerance for slippage, because the user has signed transactions expecting a precise amount in return for their input. So you saw those screenshots from the wallet when we're signing transactions. We're signing for a very precise amount of asset A in, asset B out. And the contract can only approve or deny transactions. It can't modify the output amount of a transaction based on what the new amount should be, or it can't create any new transactions based on the current version of Teal at the time that we designed this. So we need to introduce the concept of slippage tolerance. And slippage tolerance is basically this. The swapper says, I want to buy 100 of asset B, or 100 of asset A for 25B, but I'm willing to accept 99 of asset A at a minimum. But I'd really prefer 100A. So I'm not saying that I want to swap 99. I'm saying that I want 100A, but in worst case scenario, I'll accept 99. And so we say that here there's 1% slippage tolerance. So in this case, the swapper signs the transactions for the minimum amount that they're willing to receive. And then the contract calculates the expected amount at the time of execution. And the contract stores the differences as excess in local state. So this excess is like change or an IOU to the user. And then the user redeems their excess from the pool after the swap completes. So this is how swapping with tolerance is implemented. It's a bit more complicated. We're no longer just asserting that K equals the previous K. Instead, we're actually calculating what the user should get out of this swap. So we calculate the amount out, and then we calculate the excess, which is the difference between our calculated amount right now at the time the transaction is being executed and the amount that was expected to come out in the transaction. And then we store this excess in the local state of the swapper. And we also need to store this in the local state of the pool because the pool now needs to discount these amounts from the reserves. So we call these outstanding amounts. So in future reserve calculations, we discount these amounts because these are not owned by the pool anymore. These are owed to the users. And so we need to introduce this concept of redeeming, a redeem transaction, where the user submits a subsequent transaction to the pool to redeem their change or their excess that is held in the pool. And so if you've used testnet, you might have come across this. You might have seen this little box here that says you have some excess asset B tokens. You can claim them now or later. And if you click on this redeem, you sign a transaction, and then in a few seconds, you have redeemed your change. So now, hopefully, you might have a better idea of why this exists. Okay, so we'll move on to poolers and how they interact with the system. So poolers need to be able to add liquidity to pools, so they need to submit what's called a mint transaction. It's called mint because they're minting pool tokens. So by adding liquidity, they're minting pool tokens. So they make a payment transaction at the start, and then they make an application call to the stateful app, and then they transfer their two assets to the pool, and then they get a transaction that transfers the pool token from the pool to the pooler, and they submit this as a group. And then the responsibility of the stateful contract is to ensure that the user gets the correct amount. Now, the exact same thing with slippage can happen here. So again, we need to allow for slip. We have some slippage tolerance, and we calculate the amount that the user is owed, and then assign any excess, record that in local state for the user to be able to redeem later. And this ensures that the user always gets the best possible deal. So in swapping and in minting and in burning. So this this excess calculation ensures that they get the best possible deal at the time that the transaction is executed. So the user, here's an example in the UI of the user has added some liquidity and they get some pool tokens in return. Now, you might be wondering how pools are created in this system. So we said it's an entirely permissionless system. So that means that anybody can create pools. There's no special users who can create pools. The pools are not created by the Tinyman organization. So pools are created by a Bootstrap operation, which is basically just a way of creating a pool account and initializing it. So the user submits a few transactions, and one of them is an application call to the Validator App with an argument of Bootstrap. The second is an asset creation transaction to actually create the pool token, which is going to be owned by the pool account. And then the pool needs to opt into asset 1 and asset 2, and these all need to be signed by the pool logic signature. And the user can do this in the UI by clicking create a pair, and then they can create this pool with whichever pair of assets that they choose. And then once it's created, they can add liquidity to the pool just through a mint transaction. But the very first user to add liquidity to the pool, they decide the initial ratio of the assets in the pool. And in order for a user to add liquidity to the pool, they need to opt into the pool token for that pool, so that they're able to receive the pool tokens that represent their share of the pool. And then there is finally a burn transaction, which is the way of removing liquidity. And this is basically the opposite of the mint, where they receive receive asset 1 and asset 2 in return for sending in their pool tokens. And again, we have the same kind of calculations, and excess amounts are recorded and available for redeeming later to deal with slippage. And so just a note about the pool logic signature. In the pool logic signature, we have template variables for asset ID 1 and asset ID 2. And so these template variables are included in the compiled contract, and they're replaced dynamically at runtime by the clients with the actual asset IDs. And by changing these asset IDs, then it generates a deterministically unique contract bytecode, and hence a deterministically unique contract address for the pool. So if you want to look up the address, if you want to find out the address for a specific pool for a set of assets, you just need to substitute them into this contract, and then you generate the bytecode and get the hash of it to get the address. So there's a deterministic way of getting the address. So you might have noticed that there was a common structure to all of these operations. We start off with a payment to the pool to cover the fees, and then we have an application call to the Validator app, and with the first argument as the operation in question. And so this common structure is seen in the contracts, and by having this common structure, it greatly simplifies the contract code. So the overall architecture of the system is basically this. We have a single stateful app. So there's one validator app for all pools, and then each pool is implemented as a stateless contract account. And using the pool logic sig template. And so each pool opts into the Validator app, and they store some local state. And the pool also creates the liquidity token through the liquidity token, or the pool token, through the Bootstrap operation. And then the swappers and the poolers also opt into the Validator app and local state. So they opt into the Validator app so that the Validator app can store some local state for the excess amounts. Okay, so I mentioned earlier that Tinyman is a permissionless and trustless decentralized trading protocol on Algorand. So this permissionless and trustless bit. So the Validator app is entirely immutable code. So once it's deployed, it cannot change. And so this is the code that ensures that. Basically, it does not allow any updates or deletions of this Validator app. And that's very important for it to remain permissionless and trustless. If they could be updated, then the code could be changed to do something entirely different. So it is not. And the assets are permissionless. So the pool tokens that are created, it's ensured that these pool tokens cannot be frozen, and they do not have a clawback address. And these can be checked in the contracts, which are public on GitHub. So the full annotated source code is available in our GitHub repository. These contracts have also been audited by Runtime Verification. They're a leading auditing and formal verification company. And they have done a detailed audit of the Tinyman contracts to ensure that we correctly implement the AMM concept, and that our teal code is correct, that there's no security holes in it, there's no access control errors, all of this kind of stuff. And so this is very important for especially poolers to be able to trust in our system that our contracts do what we say they do. So this independent company has verified that to be the case. So I'll briefly mention that a lot has changed since the time we initially designed these contracts. So we now have AVM 1.0 and Teal 5, and these allow for stateful contracts accounts. So you wouldn't actually need to have this stateless and stateful contract combination together. You could support inline slippage tolerance with the use of inner transactions. There could be some code improvements through the use of functions, which came in Teal 4. And there's fee pooling in Teal 4, I think, which would basically negate the need for that initial fee algo payment transaction at the start of every group. But I should say that we were fully able to implement an AMM with basically Teal 3. The only features from Teal 4 we used were the wide division, which is necessary for having enough precision. But everything else was available in Teal 3, and we implemented everything that we would want to implement in the initial version of our product. So to anyone who is looking at all these new releases of the AVM and new versions of Teal, and they keep seeing new exciting things, or they see upcoming exciting things and they're waiting for that next thing, I would say don't. Just start developing with what you have now, because there's a massive amount available, and if you put your mind to it, you can really you can implement basically everything with what is available now and what was available previously. So I've showed some screenshots of the web app. Just to briefly mention that, so this is a React app. It's a responsive web design. It uses the JavaScript Algo SDK under the hood, and also the Tinyman JavaScript SDK. So the Tinyman JavaScript SDK abstracts the creation of the transaction groups, and basically encapsulates all of the protocol-related logic inside that SDK. And that SDK will be made public and open source in the coming months. We've also integrated with MyAlgo Connect, Algo Signer, and Wallet Connect for the mobile wallet. And also we used the Tinyman Analytics API to provide some pool and asset price information. And Efe is going to talk about that in the next section.
Thank you, Forgil, for this detailed documentation. Let me share my screen. So hello everyone, I'm Efe. I've been working as a backend developer for more than 5 years. I mostly deal with API design and development. In this project, I was in charge of having a robust and high-performance analytics backends for Tinyman. So before this, maybe I can briefly explain what's Tinyman Analytics. So analytics service provides statistics and visualizations over Tinyman activities on the Algorand blockchain. Therefore, Tinyman users can have better understanding about liquidities, pools, and transactions, which happens instantly. So basically, analytics service of Tinyman works as a off-chain platform which reads all Algorand transactions and records this related Tinyman information into its database. As a start, I like to show what we currently have on testnet of Tinyman and how these data are collected. So as a first screenshot, you can see the general statistics on the top at the below of busy Tinyman who is reading its newspaper. And this screenshot is from our testnet infrastructure. You can visit this website from testnet.tinyman.org currently. As you know, testnet is a different network than mainnet. Therefore, numbers in this slice are not realistic for mainnet, but they are from real running backend. On the left-hand side, you can see the total liquidity, which means total value locked in all pools of Tinyman in USD. On the middle, we have volume for last 24 hours. It means how much swap operations made in the Tinyman in the last 24-hour period. So actually, this is really important metric for the first one. The total liquidity is really important because Fergal already mentioned that we should have deeper pools for having a solid infrastructure. Also, the volume is important for poolers because poolers earn fees from each swap operation in their pools. Also, at last, we have on the right-hand side, you can see 24-hour change for the algo price. On the second section, we have asset statistics. In there, you can see list of assets which can be tradable on the Tinyman testnet. And on the right-hand side of Algorand asset, you can see that it's marked as a verified. As a Tinyman Analytics, we accept verified assets from Algorand wallet as verified. We use same data structure, the same data resource. Also, you can see that we have sum of total liquidities in all pools with the related asset as liquidity, also volume for asset and price, the current price in USD, also 24-hour change for the asset price too. Also, we have statistics for our pools, which can be swappable, and we can mint and burn some assets and do swaps. And you can see these liquidities, volumes, and different metrics from here too. Also, we show each transactions which made on the Algorand blockchain related with Tinyman at the bottom of analytics page. And you can also filter these by their type. You can filter by swap, mint, or remove. Mint shown as add, burn shown as remove in this screen. As you saw, all the values were in USD. But how? Like the question in your mind can be that does Tinyman Analytics uses external price API? Actually not. Tinyman Analytics just uses Tinyman pools for determining the US dollar prices. So let's go how the Tinyman Analytics does this. As earlier in this presentation, Fergal mentioned about the pool concept. Here is an example pool with asset A and asset B. So they have a pool has same value of asset A and asset B. Also, you know that we have stable coins. For example, USDC. USDC is one of the most common stable coins in Algorand, and one USDC coin approximately values $1. Let's say that Tinyman have a pool with USDC and asset B. Also, asset B can an algo or any asset. But for this example, let's go with the algo and USDC pool. Remember, pool always have same value of asset A and asset B. In this example, there are 50 USDC and 25 algo in the pool. It means that 50 USD equals to 25 algo. With a simple math, we can conduct that one algo values 2 USDC. So we can determine the algo price in Tinyman Analytics. But also we have assets, maybe they don't have any pool with USDC. So what about these? What about these assets don't have direct relation with the USDC? Let's say we have an imaginary asset, which is Tiny Euro. In Tinyman, it is possible to have pool with 2 Algorand standard assets, including algo. Earlier, we conducted the algo price. Now we have a pool with algo and Tiny Euro. So can we calculate the value of Tiny Euro from US dollar price of algo? Of course, yes. We have 43 Tiny Euro and 25 algo coin in the pool. It means that 43 Tiny Euro values 25 algo. So one algo values as a 1.72 Tiny Euro. Also, we know that one algo values as 2 USD. Now we can say that Tiny Euro values 1.15 USDC. Therefore, we can get US dollar values of many assets if they have a pool with USDC directly or indirectly in this case. So, long story short, for getting USD values of any asset, Tinyman Analytics accepts USDC as a reference currency. Also, Tinyman Analytics uses just Tinyman pools, not any external API or other stuff. And it calculates shortest path to USDC pool directly or indirectly. I think I talked enough about the UI and the USD prices. Let's go dive to backend infrastructure of Tinyman Analytics. As you can see from diagram, it's cloud agnostic diagram. You can see that. On the background, we have a worker which mostly integrates with the Algorand network. It makes network requests to Indexer API and AlgoD API. Therefore, we can process some blocks and get asset info or account info. And this worker collects the data which gathered from Algorand network and writes it directly to the database, our relational database. We only keep our important data in the relational database. We just use cache as for having more performant service. On the front-end side, our users, it might be like a web app user or SDK, a blockchain user. And it directly requests load balancer, and load balancers balances the load and distributes to the application servers. We can have a number of application servers. We can scale horizontally and vertically in here. Then it reads mostly from cache, and we don't have any cache in our system. It requests to our database. But in real world, in the running infrastructure, we are using AWS solutions. And on the front side of our backend, we have application load balancer, and it distributes to users to do ECS Fargate task clusters. And we have a number of application servers like Fargate task as a application server. And if in this container task, we have Nginx at the front, then Unicorn, which is a running piece of Django software. Also, these application servers communicate with database on the background, and we try to have a robust database solution. So we have multi-AZ PostgreSQL managed database, and we also have Elastic Cache Redis cluster for having quick lookups for the data. Also on the background, we have a worker, as in previous slide, and it mostly makes writes to the database. And our application servers mostly deals with the reads of the database. So on the background, how our worker works. Actually, the worker has two main responsibilities. The first one is following new blocks. And in these new blocks is there a Tinyman related transactions, which Fergal mentioned earlier. Is there a Bootstrap, mint, burn, swap, and redeem? And we check them from we know the application ID of Validator App, and we get the related transaction group, and we create related operations in our Tinyman Analytics database. Also, for time series data and other stuff, we are periodically recording pool and asset prices. For technically, we are using Tinyman Python SDK, which is also open source and can be found on our GitHub organization. Also, for making Algorand related network requests, we are using PyAlgorand SDK. Also, we have some things to implement it already, but haven't implemented on the front-end side, which are account detailed analytics. For example, you have an account on Tinyman, and you can see the fees you earned and what's the status of in historical perspective. And also we have details about pools, assets, and time series data of these. Also, I can show you some designs which are not implemented yet, but we are going to implement in near future. This is from account detail statistics, and this is for asset statistics. Also, what's our future plans on analytics? So actually, in short amount of time, we are planning to open source it. Therefore, you can run your own analytics service and do some things you like to do. Also, we are planning to make a RESTful API reference documentation. We currently have this, but it's not shaped good yet. So we are planning to make it work soon. Also, we are planning to have Analytics SDK. If you like to make some automated trading with these kind of AMFs, you can use this as a tool for yourself too. So it's over to you, Fergal.
So as Effa mentioned, we have an official Python SDK, which is currently public and open source, and it's available on our GitHub. And there is a JavaScript and JavaScript/TypeScript SDK, which is used by the web app, and that will be fully open sourced in the coming months. There is also a community created SDK already, which is really amazing. Thanks to one of our community members, he has ported the Python SDK to the .NET framework. And so the Python SDK allows you to do this kind of thing, looking up pool information and do automated swapping and pooling operations. And so you can use this for basically implementing a trading bot. Tinyman also provides Oracle data, so you provide on-chain price information, which can be read from other contracts. We'll be publishing documentation on that in the near future. So our roadmap, testnet is live. We're at testnet.tinyman.org, so you can go and check it out. Mainnet launch is soon, really, very soon. We have analytics improvements coming up, as Effa mentioned. There's some web UI improvements, and then we'll be looking to version 2 of our AMM. What can we build next to make it more efficient and more useful for both swappers and poolers? And then we'll continue our process of gradual and continuous decentralization of the project, and gradual and continuous open sourcing. The aim is to have every single component of this project open source eventually, and we aim to do that pretty quickly. Finally, we'd just like to thank everybody who supported us on testnet and provided very valuable feedback, and thanks to our community members who keep asking questions, and especially thankful to the community members who answer questions on our behalf. It's extremely helpful, so we're very grateful to those members.
Awesome job. And there's Ryan.
Yeah, thanks very much, Fergal and Effa, for bringing us up to date on what Tinyman are up to. The designs were very interesting. We know that they were done with Teal 3, and that you are looking forward to what's going to come with Teal 5 and beyond.
Definitely.
Great. You guys are doing an excellent job going over all the questions that we had in the questions tab, and I know that we probably have lots more that we could get to with our live audience here. So I'm gonna do a soft wrap here to end this session, and then we'll keep it going for a few more minutes for our live audience. All right.
By the way, one quick question that we had was Tinyman will launch. When will it launch to mainnet? Did you talk about that at all?
There it is.
There's the answer.
Okay. All right, Ryan, didn't mean to interrupt. Sorry.
No worries.
Really soon. Really mean it. We're very, very hopeful that it will be very, very soon.
All right. Well, Fergal and Effa, we're really happy that you guys could join us here on Algorand Developer Office Hours. Really enjoyed learning about what you guys are up to at Tinyman, and look forward to seeing it live on mainnet. Thanks for joining.